Okay, picking it up where we left off, we just did this problem together, the limit of tangent x as x approaches pi over 2 from the left. Turns out the next problem I have really plays off of this one well. Let me see if I can find the right page. So I'll kind of leave that. We kind of want to have that graph. Part C, what if we looked at just the limit for tangent x as x approaches pi over 2? Not from the left or the right side, just approaches pi over 2. What is the answer there? You think, oh, back here, okay, there's pi over 2. Well, this is a two-sided limit, right? So the left side and the right side have to agree. Well, the left side is going to infinity, the right side is going to negative infinity. So the answer to this is does not exist. Okay, that's kind of a nice one. We're kind of seeing some of the themes play out in different situations. I've got one more infinite limit question. It's another two-sided limit, by the way. Part D, the limit of 1 over x squared as x approaches 0. Let's see. Well, of course, if we try to plug that in, then we get 1 over 0. And if you remember, any number over 0 means it's a vertical asymptote. 0 over 0 is the whole. Something like 1 over 0 would mean there's a vertical asymptote. So we know we're in the infinite limit situation. Once we have a vertical asymptote established, then we know the answer is either infinity or negative infinity. Or I guess you could say in the case for two-sided limits, it might be does not exist if they don't agree. How are we going to figure this out? Oh yeah, there's a note. Keep in mind this is a two-sided limit, so we'll have to look at the left side and the right side separately, and then they need to agree for us to have an answer. Okay, well, let's see here. How are we going to approach this? Again, there's the graph or a table. They're equally valid for the case of vertical asymptotes. So what would the graph say? I'm just going to look at the graph. If you want to explore the left table and the right table, then you're certainly free to do that. I won't do that here in this video, though, since we've done a couple of those already, and they take some time, and I think we all agree they're a little bit tedious. The graph of f of x equals 1 over x squared looks like this. So there's that vertical asymptote there at 0, but it turns out on both sides it goes up to positive infinity. Well, that makes sense because we're talking about x squared, and that's always positive. It's actually very, very steep, even steeper than 1 over x. Okay, well, if both of them go up to positive infinity, then couldn't you say that they agree? The left side and the right side agree to infinity, positive infinity? And yep, so we can say this limit does have an answer. It equals infinity. Okay, very nice. Well, this has been quite a discussion on the introduction to limits. We've got one last topic to close it out. A few of the sections that we see here in the first chapter, they end with a major theorem. And so this is our first theorem in the course. It's called the Squeeze Theorem, which is kind of a peculiar name, but you'll see where that comes from. So what is the Squeeze Theorem all about? Well, of course, it has to do with limits. Here's what it says, and then I'll explain further before we see an example. If f of x is less than or equal to g of x, which is less than or equal to h of x. So we've got these three functions, and we see how they're related. F of x is always smaller than g, is always smaller than h, or maybe they're equal. And we know something about the limits of f of x and h of x. So the limit of f of x as x approaches a equals L. So we don't know those numbers, but okay, we would be told that in a problem. Or we would know that in a problem. The limit of f of x as x approaches a equals L. And that equals the limit of h of x as x approaches the same value a. Then what can be said? So it turns out we know something about the limit of g of x as x approaches a, and that will equal the same thing, the same number L, whatever that is. Okay, so it turns out in calculus, when you see theorems, they can be a little bit shocking. This one is maybe not so bad, but as we see more and more theorems, they're going to seem really heavy. They're going to seem very rigorous is the word. We really step up the amount of rigor that kind of goes along with the concept intensive side of calculus. However, once you explain things in terms of like maybe a graph, then a lot of times they seem a lot less intimidating. So that's what I'm going to do now. Let me explain the same theorem graphically. So there's more to write. I'll fill in the rest of it after I set this part up. So imagine this. I've got f of x and h of x. Okay, so I've got this, xy plane. Let's say there's a, and f of x is just going to be cruising along, and we can tell, nothing unusual about it, we can tell that the limit as x approaches a for f of x is that point right there, and that's equal to L. All right. Then we've got h of x. So h of x is always bigger or equal to than f. So h is up here, and it's kind of cruising along, and its limit is the same. So as x approaches a for h of x, that limit equals L as well. So there's L, right, that y value. So it turns out they equal each other for just that one point. Okay, then we see, all right, f is on the bottom, h is on the top, g is stuck in between. So g is going to kind of be cruising along like this, but as it moves, remember, it's always trapped between f and h. So as g comes along, if these start to squeeze together, then g has to squeeze, and it has to push through kind of like that. And there's g of x. Well, what just happened? If the bottom and the top squeeze together, then this function has to squeeze between them. And well, doesn't it then also have that same limit? Doesn't the limit as x approaches a for g of x have to equal that same value of L also? And yeah, it's got nowhere to go. It's being smushed in between those two. Of course, that limit has to be the same number for g. Okay, what will this look like in an example? The squeeze theorem allows us to take limits of things that we wouldn't be able to do otherwise, or maybe at best we'd have to resort to a table. And as we said before, we really don't want to have to resort to a table if we don't have to. For vertical asymptotes, they're okay. But certainly in no other situation do we want to do that, unless we absolutely have to. Okay, so the squeeze theorem gives us another opportunity. Let's look at this. The limit as x approaches 0 for x squared times the cosine of 1 over x. You're like, oh my goodness. I mean, think about if you tried to plug in 0, this is going to be terrible. This is terrible. If you plugged in 0, for 1, you've got the cosine of 1 over 0, right, which is undefined. Not only that, though, but you're multiplying it by 0. 0 times, it's like 0 multiplied by undefined. Like, what? Okay, this is not good. Right, like, is the answer 0? Wait, but that's not defined, so the answer is undefined. You're like, no, but there will be an answer to this, so it's not undefined. Yeah, okay, yes, you get it, you get it. This is just not a good, I'm going to erase this because I don't want to confuse people too badly. Okay, so it turns out the squeeze theorem can get us a definitive answer, no doubt about it, and it's pretty nifty. Okay, so what's going on? Now you notice, hey, they only give us this limit. The squeeze theorem talks about an f, a g, an h, you know, these limits. Like, what are we going to do? Okay, follow with me here. So what you see right there, the one that we're given, that's g. Think of that as g, okay? That is the function that's going to get squeezed in between two other functions. All right? We're going to have to create or come up with the function for f of x and h of x on our own. And there's kind of this path we're going to walk down to do that. Okay, how are we even going to get started on what f and h are? Here's what we're going to do. You notice that g has cosine. Okay, so let's begin with that. Cosine of 1 over x. Would you agree with this statement right here? From your understanding of trig, would you agree with that? That cosine of, well, it happens to be 1 over x, but that's not even so important. The cosine of anything is always somewhere between -1 and +1. And hopefully you agree. Yes, the cosine of anything is always stuck between -1 and +1. It can never be outside of -1 or +1. It could equal them, but it can't go outside of that. Okay, so that's where we're going to start. Say, okay, I can take that cosine and just begin. So now we see the three parts. We're not there yet, but we're building towards it. Now what are we going to do? Well, we notice, okay, but the g that I'm after, it's not just cosine 1 over x, it's got this x squared as well. So here's what we can do. Multiply all of these, all three of them, by x squared. I'll multiply in here, but then that means I got to multiply these as well. And we're going to realize this. I mean, if this is true, doesn't this have to follow? Multiply each one by x squared. That's a little bit. Let me line that up a little bit better. X squared. Now this can kind of be confusing for a lot of people. And you're like, what's happening? Hey, I'm just building g of x. So I took the cosine. I noticed this true thing about it. And I said, okay, but I also need an x squared. So let's multiply by x squared. So I got to do that all around. And now I can see my g of x clearly there in the middle. That's what I wanted it to be. And then down here is my f of x, and up here is my h of x. And g is caught in between. That's pretty cool. Okay, so what do we do with that? Well, the theorem said that if this is true, if that relationship is there, and if the limit for f is the same as the limit for h. You're like, what is that all about? Okay, so go back. The limit that we're concerned with is x approaches 0. So let's take the limit as x approaches 0 for this one and for this one. And here I'm actually going to show you all the rest of my work, but I'll talk it out, of course. So I'm going to take that limit as x approaches 0 for the f of x. And, well, if that's negative x squared, I can just plug that right in and get 0. And I'll take the same limit as x approaches 0 for the h. As x approaches 0 for x squared, well, I'll plug that 0 in, and that answer will be 0 as well. And we see, oh my gosh, when I take the limit of the f and when I take the limit of the h, I get the same result. This limit of f and this limit for h are the same thing. And I know the g is squeezed in between. So what's happening is the f and the h are coming and they're squeezing in at 0, and actually the y value is 0 as well. So what does that tell us? The limit as x approaches 0 for the g function has to equal that same number, 0. And we got our answer. Okay, this is really cool and convincing if you check it out on Desmos. So